So the chloride will attack the concrete and then go to the armor after a while, steel reinforcement, and then you may have, of course, corrosion and failure of the armor, and also spalling, of course, before the armor fails. And this bridge was used as a kind of a test site because they had a large number of samples, chloride profiles, surface concentration. They also looked at different repair methods for this bridge and came up with comparison of different types of repair methods, which is not the subject today, but that's what happened with this bridge. So the test we are going to look at is diffusion coefficient, surface concentration, concrete cover, which was measured by a cover meter to see the variation of the distance from the reinforcement to the surface of the concrete. So this is now the cumulative distribution for the probability paper for the diffusion coefficient for one of the columns based on the tests. And you see we have compared different types of probability models: normal, gamma, gamma, y log normal, and then the regression coefficient, which you see in the column to the right, tells you the goodness of fit, and we see that 4 of the 5 models give pretty high values of the regression coefficient, 0.99, 0.98. The maximum possible is 1.0, so this is a pretty good fit to the data in probability paper. The gamma is not so good as the other ones. The mean value and standard deviation of the coefficient is also given in the columns here. So this is now a probability plot for the y-wall. To give an example, and you see that data points they fall pretty much on a straight line. Of course, there is some bump at one point, but generally it implies that the y-wall model would be something you could use for statistical analysis of these data. This is now the histogram, and again you see that it's some peaks and valleys, but overall we see that the smoothed probability model would fit the histograms in an okay manner. Now this is the surface concentration, not the diffusion coefficient. And we look at different parts of the bridge, is that there are wide differences, like the front side towards the wind has less surface concentration than the leeward side, and this is due to the rain and the wind, which washes the front side. While the leeward side you have turbulence, which means that you have chlorides which are put on the surface of the leeward side, more than the front side. Now again, you see we have pretty high regression coefficients, 0.92 to 0.98, and for this case you have the log normal, which is slightly better than the gamma, which is surprisingly maybe the second place. Again, this is now the probability paper straight line fitting by a regression line, so we see again that the fit is not too bad, but still it's not perfect. So these are now the statistical distributions which we apply for the lifetime estimation. This is now the variables which are included, the surface concentration, and this is kind of an averaged value for the superstructure, because you also have differences, as I mentioned, on the front and leeward side. Diffusion coefficient, alpha factor, we come back to that. It depends, it tells about the time variation of the diffusion coefficient. Alpha factor higher than 1 tells that the diffusion coefficient is decreasing with time due to the blocking effects. But here it's 0, so it means it's constant with time. Initial concentration at the armor is based on literature study, 0.015% of concrete weight. Concrete cover is 23 millimeter on the average, but the standard deviation is pretty high, 6 millimeter. And the critical chloride level, also based on literature survey, 0.18%, and the standard deviation of 0.06. Model uncertainty, optimistically put at 1.0, and standard deviation is varied at 0.1%, and 10%. The results I will show are based on the 10% variation. So this is the reliability model. We have the concentration at the armor as a function of time. So if you put x equal to the distance from the surface, we get the location of the steel armor. We have the initial concentration. We have the difference between the surface concentration and initial one, which is a driving factor. You have the arrow function, and you have the distance again to the armor, and then you have diffusion coefficient and time and square root of that. So this is the how the concentration is changing with time, and when this reaches the critical level, then you have failure. So it means it's initiation of corrosion. It is not like ultimate capacity or failure of the armor. It is starting of corrosion at the armor, which is the criterion here. Now for the columns, also we have a similar table. I will not go into because the results I will show is for the superstructure. But again, you see that we have two values for the mean values for the surface concentration. This corresponds to the two different columns, 0.25 for one of them, and then twice as high for the other one, 0.5. Also standard deviation is very different, but the COE is pretty constant. So this is now the cumulative distribution of the lifetime, and lifetime here, as I mentioned, is start of corrosion of the armor. Based on the input statistical model, this is for the superstructure, and now this is with the time varying. Let's see, I think this is probably this is with time varying diffusion coefficient. So we see that we have after 80 years it's 0.18, but we also see that probability density has the peak at only 6 years. So based on the first order reliability method, there is a peak most likely on time until you have start of corrosion, but the upper tail is very slowly decaying, so it means there's very high uncertainty in the predicted time until you have start of corrosion. Now this is again with a constant diffusion coefficient. So here we have 0.4 after 8 years, but also the peak is located at pretty much the same spot, around 6 years. But we also see that now the upper tail is more faster decaying because the time-dependent diffusion in the previous figure means that diffusion coefficient is slowing down. It becomes lower with time due to blocking in the concrete. So this is now exponent of 0.4 on the, it's roughly square one inverse square root of time. So this is now the one site, one spot, one representative spot type of analysis. Now we go to the system analysis, and this is now simplified. We say it's a series system with 90 components. And failure now means that if you have initiation of corrosion at a single spot on these 90 sites, then you have failure. So it's really a very strict criterion because, of course, start of corrosion is not, it's very reversibility type of criterion. It does not ultimate capacity of the girder. Then the surface chloride concentration here is mean value of 0.14, standard deviation of 0.028. So we have only a single variable to look at 90 components. It's in order to have affordable computation times to look at the behavior of the system, and also this is now after 30 years without any monitoring of the bridge. And what does this figure show? We see that the idea here is to idea here is to perform simulation at low probability level, high probability levels, and then extrapolate the confidence span to lower levels. So that means do simulations here, so you save time because you can tell what's happening at the so-called scaling factor lambda is 1, which corresponds to the true failure function. So this is now some kind of enhancement to color where you save computation time by simulating here while you predict what's happening here. So typically you can save computation times by a factor of 10 for the case we are looking at here. Now we can also look at the effect of knowing the surface concentration for half of the component. That means for the 5 components where you have information about the surface concentration that is smaller than 0.196%. And again, we see that there is some scatter in the parts where you have high probabilities, but the confidence band is stable when you extrapolate to the full limit state function for the system. Or it's really 90 limit state functions that comprise the system for a serious model of the bridge. Also, we can look at having a more strict criterion for the observed surface concentration, 0.18, and we see that now we get smaller failure probabilities because you know the concentration is smaller than for the previous case. Then we can look at the system reliability analysis, and this is now as a function of time. So we see that now we have inspection, no inspection, and we have correlation coefficient, this column. So we go from independent components to full correlation, and in between there's 0.5. And also you can have monitoring, that means you observe half the components, 45 sites, and you have zero correlation, 0.5 and 1.0. And the point is that the effect is highest when you have high correlation. That means if your correlation is 1.0, it doesn't matter if you have 90 components or 1, because all information is contained in each single component because they are fully correlated. So it's really not a system with 90 components, it becomes a system with 1 component. So then you have a large effect of having information about reduced surface concentration. So we go down to 8.6, 10 to minus 9 for the 30 years, and also for the other durations up to 90 years, we have a very strong effect of doing monitoring. But 0.5 is not that strong correlation. Observations are that you need a correlation of 0.8 or higher before the correlation effect come into play on the system reliability values. Now this is again a number of components you inspect, 1 up 5, 10 and 45 in the upper row. Then also we have monitoring, no monitoring with correlation, zero correlation and full correlation. And again we see that the effect is strongest when you have full correlation, and that of course is the case both when you have monitoring and no monitoring. You have a reduced failure probability for the system. And also we see that for full correlation, it doesn't matter if you observe on 1 component or 45 components, because they are all identical. So these are now and I think this also confirms general observations on system and reliability analysis, that if you have zero correlation, the effect of inspection and monitoring is less than if you have very high correlation between the failure function for the different components. So, to conclude, we have looked at probabilistic models based on full-scale measurements from this bridge. So I think for a while, at the point in time, this bridge looked like a Swiss cheese because there was many holes from the coring of the bridge, but then of course they fixed it afterwards. So we also have models that apply to the diffusion coefficient, chloride surface concentration, concrete cover, which are focused on this study. Also, we performed probabilistic lifetime calculations for a single site to start with, and then we looked at system reliability effects by an enhanced Monte-Carlo simulation method, which has also been applied to other system models for other applications previously and found to be stable and efficient. Computation time is typically savings by a factor of 6 or more. But of course, there are future research topics. As I mentioned, effective correlation between the system components. That's a general issue, especially if you go to systems with parallel and series components in combination, because this was a pure system series model. if you look at ultimate limit state, you need to combine with also parallel systems, because you need several sites to fail at the same time, and then you have a serious system in the longitudinal direction of the bridge typically. So we should also look at the effect on non-identical system components, for example, surface concentration that is changing in space, and probably also in time if you have storms, sea spray which washes and winds that washes away some of the chlorides, it will change with time. Also, we should look at combination of parallel and series system models for the entire bridge system, and also, as I mentioned, ultimately mid-state criteria in addition to serviceability criteria. I think there have been also several studies on that in literature, but of course for a bridge like this it could be interesting to do the same for this particular classes of bridges which are quite common along the coastline of Norway. So that is what I had to say. Thank you for your attention so far. I will try to answer questions. Thank you.
From Zagreb. I have a question related to time-varying diffusion coefficient. Did you take into account the cracks in a concrete cover in a time-dependent diffusion coefficient, and also concrete quality, such as content of cement or water-to-cement ratio?
Yeah, I guess the concrete quality will influence diffusion coefficient, the value of that one, and I'm not quite sure about what mix was supplied here, but I could find out. Also, of course, when it comes to the concrete cover, that has a strong influence, and we saw the mean value here was around 0.23 millimeter, which is not very much, so I think this was a learning also from this particular bridge, that it's not sufficient really to have a bridge which has sufficient time until you start corrosion at the armor. But of course another issue is the speed of the corrosion of the armor, also when you really have spalling and failure of the armor. But of course the concrete mix, I think, has a very strong influence. What we also have from our studies, very strong influence on the diffusion coefficient. And of course we saw also here the time until you reach the critical concentration of the armor depends strongly on the distance, as we saw from this arrow function. So it's not a linear relationship, but it has a very strong influence. So we also did some studies to find out what would be sufficient cover. I think it was in the order of twice this value, 5 centimeter or something, or maybe even more. So. And even other structures at the coast of Norway, old quays where ships come in, and also you have a lot of sea spray. They have sometimes even less cover. They has had a lot of problems with the chloride attack and spalling, and they had to repair it or replace the quay. So it has been a learning process from the coastal regions for chloride attack. Yeah.